Okay, so let's test out and see if this works. Hopefully it does. Um, Last time the video, well, actually the live wasn't doing good because again, uh, there was a problem of the uh, microphone and okay, there we go. It works. So let's see if it's going to work with my uh, headphone. Because last time when I put the headphone on, there was an audience told me that there was no sound for the entire live. So let's figure it out. Okay, testing. Okay, one, two, three. All right, good. All right, so welcome back to my channel. So so last 2 weeks we actually had done the stream as well. However, because of technical issues, um, the previous one actually had no sound at all. Um, and we somehow had to stop the live stream because no one could hear what I was saying. And then 2 weeks ago, when we were trying to finish the last couple problems in chapter two, unfortunately, we also have lost the my Wi-Fi here, and it got disconnected. And eventually, we wouldn't be able to explain the last part of the last problem in chapter two. So today we're going to continue chapter three. Yes, the last two videos, or more precisely, the last two live streams, has changed from public uh, to unlist. So I'm not sure if anyone will be able to see it still. But either way, that's not really a big deal, even if you cannot read and see it. It's because again, I'm going to go over those problems that we actually did in the last two live streams quickly before we actually continue to uh, talk about the coming up problems in chapter three. So here we go. Wow. Okay. Yeah. So back to the live stream here of the chapter, as well as when we actually went back to problem 3C to go over the solutions. So let's see what is going on. Now this time somehow it cannot really show the, there we go. We can actually show this, the share screen of the document. So going back to the question, in chapter 2, problem 3C, which numbers C can appear in a primitive Pythagorean triple A, B, and C? Well, eventually we actually have to use the solution we found on the book. Well, it's not complete a solution, but more likely is part of the results from the chapter right before the exercise problems that we eventually set A, B, and C to be uh, C equals S squared plus T squared over 2, A equals S times T, and B equals S squared minus T squared over 2, respectively. For S and T positive odd integers with the conditions S is strictly greater than T, and the greatest common divisor of S and T. Other words, the greatest the common factor here is going to be equal to 1, or in another way of saying, S and T are relatively prime or co-prime if you know the term. Then we of course will be able to prove that C squared is equal to A squared plus B squared by substituting the values of A, B, and C respectively, and then of course with the manipulation of algebra, and then we actually will yield the results as we desired. So this one is actually a lot more trickier than part A and part B, where finding the possible odd numbers A and even numbers B, like in a quite clean way. Um, but anyhow, we actually get our solutions that we need. And for number 9C in this chapter, which is asking uh, converting some of the pairs from the Babylonian numbers to decimal numbers, or the number system that we actually use in daily life, and of course compute the value of B to show that those A, B, and C actually will form a Pythagorean triple, where these A and C values are the second and third column of the Plimpton 322, or the tablet, the tablet that we actually found on the online, also mentioned in the textbook, which was found by mathematicians and studied about it. And shortly saying, we actually can convert, of course, we actually can get the A and the C values of each row. Besides trying to understanding those Babylonian numbers, we can also try to look at online, of course, to save our time. And of course, we can also try to use use some well yeah so yeah some programming like Excel, whatever, to actually helping us to converting those Babylonian numbers into decimal numbers, as well as setting up our formulas, b squared equals c squared minus a squared, to actually find out the values of b squared for each row, and take the square roots to get the value of b, to show that most rows actually provide us the setup of Pythagorean triples, such as b as some positive integers as we expected, where there are a few rows or few lines that actually don't match, such as rows 2, 9, 13, and 15, where rows 2 and 9 actually gives us non-perfect square for b squared. Meaning that b is not it's not an integer and not satisfying being a Pythagorean triple. And of course, we also have rows 13 and 15 giving us the value of b squared as negative, to imply that b is actually an imaginary number instead of a real number. So it's not even close to being a positive integer in this case. Well, and if we try to look up those articles online, or trying to look up on Wikipedia, they also kind of explain that it is possible that there could be a typo when the Babylonian people recording those numbers, such as having typo for the A value or maybe the C value, or when we are trying to analyzing the A value, the A and C values from the tablet, we actually might have a problem that the way that they write is a little bit unclear. Um, that we might actually misunderstanding because they don't have placeholder as explained, and causing the conversion being a different number as we are expected. Okay, and of course, in those cases, we won't be able to get our b value being a positive integer in this case, and therefore well, we believe those are typos, and then we actually could kind of figure out like how to fix those. Well, like if we try to read some of the articles, they actually provide those corrections, so that if we try to apply the Pythagorean theorem there, we'll be able to yield b values being positive integers. Okay, and then the way that they write the Babylonian numbers, well, the symbols, are actually not too far off from what the actual value should be. Meaning that some of typos might be just missing like one more symbol of a one, or maybe there's a placeholder that's missing, or like they didn't spread out wide enough to to get the digits correctly, things like that, which again causes the problem of having the errors. Okay. Now, anyway, we actually finished chapter two, and as we move on to chapter three again, which is related to Pythagorean triples still, and the unit circle this time. Last time we went through pretty much just a solution of 1A. We didn't really go through much because again, thank you for the audience who actually uh, remind me that my microphone wasn't working properly last time. And that's again the reason why we actually end the live stream like all of a sudden. So problem one. So in this chapter, we actually have we actually have rewritten the formula of A, B, and C, and using instead of using S and T, we use U and V instead. And instead of having 2 in the denominator, we actually multiply all the values by 2 this time to get the formula A, B, C to be U squared minus V squared, U to UV, and U squared plus V squared respectively. And in this case, we are now not limited for U and V be positive integers odd numbers anymore. We can actually plug in any positive integers, such as U being an even number in this case, where we still have the condition that U has to be strictly greater than V. And of course, that has to be true because otherwise the first term, A, which is equal to U squared minus V squared, is going to be negative if we have a V is greater than U. Or of course, if U and V are the same, we'll end up being a 0 there, which is of course not satisfying being a Pythagorean triple. Okay. Now, of course, in this case, we no longer have the condition that such Pythagorean triple is primitive, meaning that they actually might have common denominators here. And again, we're going to show that this is going to be true for several cases. First of all, in problem A is asking that if U and V have a common factor. Of course, in this case, we're assuming that this common factor is strictly greater than 1. Otherwise, it will just again going to end up with the case that we have in last chapter. Then explain why A, B, and C will not be a primitive Pythagorean triple. And here comes the solution or the proof. Okay, so suppose that there exists a D, which is of course a positive integer that is strictly greater than 1 or 2 or bigger. And we call this D to be the GCD of U and V. Then of course we can rewrite U and V in terms of D by saying that U is equal to dm and V equals dn for some positive integers m and n. And then now we can actually try to rewrite A, B, and C in terms of D, M, and N respectively. And for all three values, A, B, and C, we can always factor out the D square, meaning that D square in fact is gonna be a common denominator of A, B, and C, showing that the GCD, in fact, it could be greater than or equal to. It's not necessary to be equal to. It could be greater than as well, because we don't know whether or not m squared minus n squared, 2mn, and m squared plus n squared. These three values actually will have common factor other than 1. Okay. The minimum is definitely 1, but it could be possible that they have common factors that are 2 or bigger, meaning that the GCD of these three parts inside of the parentheses would be at least equal to 1 or greater than or equal to 1. Then with the d squared outside, meaning that's the GCD of all these three values would be at least d squared, or we would say that is greater than or equal to d squared. Okay, it could be d squared, it could be 2d squared, it could be 3d squared, and then the number in front of the d squared, no, the coefficients is actually be the GCD of the three expressions inside of the parentheses. Okay, so if we have that, then by definition, uh, we have A, B, C, the Pythagorean triple. Well, we don't really have to mention it, but we know that it's a Pythagorean triple. Triple, the ABC is not primitive. And again, when we say that the Pythagorean triple A, B, and C is primitive, it actually means that the GCD of A, B, and C must be equal to 1. But since we have a contradiction here, that the GCD is greater than or equal to d squared, which is strictly greater than 1, we actually have a contradiction to be a primitive Pythagorean triple. And that's how we actually end our answers. Okay, so let's refresh it to come up with our conclusion here. All right, excellent. Now, part B. Find an example of integers u, v. Again, positive integers u and v, where we still have the condition that u is strictly greater than v. And then they do not have a common factor. In other words, the GCD of u and v will be equal to 1. But then this Pythagorean triple is still not primitive. Well, in this case, we actually can take anything as long as u and v are odd. Okay, so for instance, here comes our solution. So begin solution. So let u be equal to 3 and v is equal to 1. Again, we need to satisfy a condition that u and v are positive integers and u is strictly greater than v. Well, we have that here. Now, what's going to happen? Then we're going to begin and see that the first part, u squared minus v squared, is going to be equal to 3 squared minus 1 squared, which again is going to be equal to 9 minus 1, which is equal to 8. Good. Now for the second, the b value, 2uv, is going to be equal to 2 times 3 times 1. Now this is actually quite important because we actually have the condition that u and the GCD of u and v is just equal to 1. Okay. Now the goal here is to show that there is a common factor between these three values a, b, and c. Clearly, b is an even number because we actually see a factor of 2. Now, why do we want to set our u and v to be odd? Because we know the square of an odd number is an odd number, and then odd minus odd is going to be even. Odd plus odd is also going to be even, meaning that they're both even. So all three values a, b, and c are going to be even in this case to show that there's a common factor of 2, not just 1, meaning that it's not primitive by definition. So if we continue our work, we get 2uv is going to be equal to 6. And last but not least, we have u squared plus v squared, which is going to be equal to, again, as we substitute it, we have 3 squared plus 1 squared. And again, 3 squared is going to be 9, and 1 squared is just 1. So adding them together, we get 10 here. And this implies that implying that the GCD, the GCD of A, B, and C is gonna be equal to, again, the GCD of we have 8, 6, and 10, which is gonna be equal to 2, and which is greater than 1. Okay. So we can conclude that, hence, well, we actually get our conclusion. Or hence, this Pythagorean triple with that satisfies our condition is not primitive. Okay, so here comes our solution. Let's take a look. So we have our solution here. Okay, we have our condition that u is greater than v, and they're both all positive integers. That's all the conditions that we need. And then as we substitute it, and we found that the GCD of these three values, A, B, and C, actually end up to be 2, which is strictly greater than 1. Again, if it's strictly greater than 1, it's not primitive because they're not relatively prime anymore. There we go. Part C. Make a table of the Pythagorean triples that arise when you substitute in all values of u and v with 1 is less than or equal to v, which is strictly less than u, which is less than or equal to 10. Okay, so what we're gonna do? Well, we're gonna make a table here. So let's see. If we're going to make a table, press too many times. We're gonna begin our solution by making our tabular, and of course we have to have we can just do the following. So we have, let's see, what is it? Make it figure arise when you substitute all values of u and v. Okay. So let's see, we have 1, 2, 3, 4, 5, 6, 7. Let's do 6 here. I'm gonna split it into 5 and 5. So you guys are gonna see what I'm saying. Okay. So of course, first we actually need the H line here, and then after that, we're gonna start it. Now for the first row, we're gonna put down u, and then backslash v. Okay, so actually, yeah, we're gonna do it this way. And again, because we want our v, we want our u value is gonna be greater than v value. Then what we have is, of course, we have v is gonna start with 1, 2, 3, and then 4, and then 5. Now again, here's the reason why I'm going to write it this way, because instead of having all the way to 10 for the v value, I'm going to end at actually, maybe I should switch it the other way around. I'm gonna do v here and then gonna do u here, and of course u will start with 2, not 1. Which actually matters in this case, because now I actually need to adjust it. Now, here's the reason why I'm going to write out up to 6. That is because, and then start from the second row, because for the v value we are going to start with 1. Of course, we're going to do. Let's see. I have 1, 2, So this is a 2 here, a 3 here, and then a 4 here, and then 5 here, and then 6 here. I believe this should actually work. 5, 6. Actually, we're separated into 6. So again, it is kind of hard to figure out why this is going on, because inside of here, I'm going to put down the set of Pythagorean triples, meaning that I'm going to put down 3 values, and it's gonna actually take long for how should I say it, for each row here. So this is what gonna happen. And then again, so we can actually try to visualize it. Actually, I'm going to put a few more rows here. Okay, so in between each line, we actually need a horizontal line so that we actually can see the separation like on our table later. Okay, now this is what gonna look like. So far, we actually don't know what's going on yet, but if we recompile this in parts, and then we'll be able to see what is going on. So here we go. If we recompile it, we actually get a table that looks like this here. It doesn't really look like a lot, but then I'm going to, maybe I should just make one more line here. Begin, and then I'll say something like, here is the table of the, well, we're just trying to copy what the question is asking in our answers. That arise when substituting in all values of. Now you won't, like, when you're trying to answer a question like this, you don't have to worry that this is not really a plagiarism, but we're just trying to not even have to rephrase it. We just like go directly answering what the question is asking for. Okay, then of course we should use a colon here to show that what we're gonna get. So it actually looks nicer. The table is actually gonna be down here. Now, this is also a reason why I'll actually separate the tables all the way, instead of like going all the way to from 2 to 10 horizontally. We actually pause at 6. Maybe we actually need to adjust it later too. But here's the reason, because now we're going to fill out every single cell. So let's start with u equals 2 and v equals 1. Okay. Now remember, we have the Pythagorean triple formula here. So the a value is going to be equal to u squared minus v squared. Okay. So I'm going to open another table real quick on Google, which is actually the Excel, or they call it the Google Sheets. Now I'm going to use a untitled spreadsheet that I actually made. Actually, no, this is something different. Okay. So this is what we're gonna do. Okay. So we're gonna type in our u values. Okay. And then we have the v values here. Okay. Now keep in mind the v values can start from 1. Okay. But the u values actually start with 2, like the following. Meaning that if we are trying to do this, we just need to go all the way to 10 here. Now here is 1, 2. If we keep going, we have to go all the way down here. Okay, good. So what we're going to do, well, we're going to make a table, right? So we're going to make a couple of things. First of all, we see a u squared, and then we see a v squared there. Okay. So we're going to make a table of here is u squared, Again, we're not using this in the entire time. We're just using this as our tool, helping us temporarily. So the form doesn't really matter. So we have to take this, nope, this cell actually, and then raise it to the second power to get this. And then if we drag down, we get all we need. And then next we have v squared. So of course we will have something like this being squared. So enter, and then we actually do auto, and then of course we need to drag down one more. Okay, good. So what we're gonna do? Well, we have to actually pair them up. Uh, so what do we need? Well, we actually need first of all, let's figure out the a values here. We have the a value is gonna be equal to, again, it's just an expression here. It's a formula. A is gonna be equal to u squared minus v squared. Okay, so starting off with the a value here, we're going to put these values. So actually we can do the following: 1, 2, and again this is for the horizontal is the v, and then the vertical is just the u values. So this is gonna be equal to this, and then we're gonna drag all the way down. Okay, to make our table clean, where the v value is gonna be like here. Okay, and again, do we really have to do those parts aside? We don't really have to, but might as well. Doing all the way to 10 actually. No, I need a 10 here. Okay, here we go. So what are we gonna do? Well, keep in mind u value is actually the vertical, and then the v value is horizontal. So here we have this is gonna be equal to so we actually need the square of this value, where g is actually the column, which is not good, which is fixed. So we actually need this dollar sign, so that even if we move to the right, it's not going to change. And then we need to square this, and then we're gonna subtract this value here, which the is not going to change. It's always row 1, and then we need to square it. So shoot. So it's going to be like this. So if we do the autofill, it's going to be like the following, and then oops. And if we do autofill for all these here, we get something like this. And again, in this case, we actually flip the u and v value. So we actually need to be need to be a little bit more careful. Or I can actually take out this row here. Actually, no, I'm gonna delete this column. Right, reset this. Good, and then I'm going to insert one row above, which is called 1 here. And again, and then it will be the other way around, actually. So we actually need a correction here. Let me delete all these. Oh, okay, let's try to fix it real quick. Okay, let me remove this thingy then. And then I'm going to fix all these. So we actually read it a little bit wrong here. So maybe I should start with a 2 here and then a 3 here. Let's redo this thing. So we get all the way to here. Actually, we don't really need this one. Just delete the cell, and then we're gonna add one row here above, and then put a 1 here. Good. Now again, we actually just need the formula, but this time we have the U is actually horizontal and then the V is vertical. So what we need is we need this value, and then we always have we always take cell well the first row here. So we're gonna fix a 1, we square it, and then we're gonna subtract this here, but we are always fixing the G column here, and then we square it. So we get this, and then we autofill, we actually get this, and then if we extend it, we get all the way to here. And again, we don't really need this, delete this cell here. No, we actually can delete this, and then this we can cancel it. And then again, we can now just bring the whole table out. Now, what does this do? Well, it's actually giving us all the A values, right? Now, of course, we actually see the A values could be 0 or negative, but this again, because we have 0 if U is equal to if V is already equal to U, and then we have negative if V is greater than U, and then we're not going to take those, of course, because we need to satisfy the condition that U squared, well, U has to be greater than V. So in this case, we actually get what we need. We actually got what we need. Excuse me. So for the first row, from 2 to 6, we have 3, 8, 15, 24, 35 respectively. So we're gonna go back to, and then we have 3. Let's see, we have a 3. We don't need this yet. And then let's see, we have short-term memory here. Let's try to pull this out. Put this here. Let me shrink big. Okay. Let me adjust a little bit. I'm going to do the following. For my own sake, I don't have a second monitor. It's gonna be hard for me to keep track. So we have 3, and then I'm going to put it sideways like this, temporarily, so that I can actually easily copy down those values. 15, and then we have a 24, and then of course we have 35 here. Now, of course, starting from the second row, the first cell doesn't make sense. We can just put NA, not satisfied. Oh no, not satisfied. Not applicable. And then similarly, we have NA. I actually keep forgetting if it's a backslash or just a slash, but I guess it doesn't really matter in this case. It's not going to affect that much. We're just doing math. Now, row 4 is gonna have 2, 3, and 4 not applicable. And similarly, the last row, we actually have all of them not applicable. Now, in this case, we in fact just need the 3 separate tables instead of all 4, because we can clearly see that for V is 6 or greater, we don't need any. Well, actually, in fact, I can actually leave row 5 for a second row, but it doesn't matter in this case. Well, when we won't be able to get V is going to be equal to 10, because in that case we have force U to be just 11 or above. But that actually is our range. So now is if we're going to see it, we actually get now let's compile it and see what's going to happen. Well, we have a table that is not too large, but large enough, and then we can actually see that if we squeeze in the B's and C's value on first row, it will actually be wide enough, and we won't have room to fit in anymore. And that's why we actually need a few more. Anyway, good. So then I'm going to copy this, and then for the second table, we still have 1 through 5, but then here we're gonna end up with let's see. I actually don't need these many. I just need something. Okay, I'm going to make a few more tables then. So I'm going to make a second tablet here. Anyway, tabular. And then for the second tabular, it's gonna look very similar to this. Oh no, that's not good. Okay, copy. And then I'm gonna paste it here. Now, of course, this time we don't need this many because we have 7, 8, 9, and 10. So we have 4 values remaining instead of 5. So we can actually, well, we still need to change it here. 7, 8, 9, and 10. And of course, we don't need a 6 again here. So we actually can take 1 out on each row. We saw 1 through 5 though, by the way. So we have this here. 1, 2, 3. 1, 2, 3. Oh, I actually took too many away. Okay. Oh wait, hold on. There's an NA. I didn't see it. All right, here we go. So I actually don't need this. Just remove it, and then again I can remove this, and then I can remove this entire thingy. But again, now we actually need to change those values because we actually found it. Here, 7, 8, 9, and 10. And of course, each row is going to look the same. There's nothing that is not applicable anymore. You have something like this. So this work is repetitive, and we actually can see that if we're trying to do it quickly. Hopefully I can do it quickly though. Let's see. So I'm going to move it down here again. So for row 2, we have not applicable. And then this is a 5. Then we have a 12. And then I'm going to make it quick. 21, 32. The third row, we have a 7, and then a 16, and then a 27. Fourth row, we have a 9, we have a 20, and then the fifth row is just simply 11. Okay. Now, if we are if we're moving on to the other parts, we have let me see. So if we are going to part of the table here, we have on the first row, row 2 in this case, which is for v equals 1 here. We have let's see, we have the first one is 48, 63, 80, and 99. Okay, and then similarly we have 45, 60, 77. And of course, we should expect that these values are supposed to get smaller and smaller. Again, that should make sense because as the difference of u and v are getting smaller and smaller, then the difference of the squares should actually get smaller and smaller as well. So we can actually see that as we approach to as the table is going downward, those values are actually getting smaller. And then we have this. We have what is it? 55. We have what is it? 72, and then 91. Okay. Row 4, we have 33. We have what's it? So 48, 65, things like that. 84. And last but not least, we have 24, 39, and then we have 56, 75. And as we mentioned, we actually need one more table. And then in this case, we actually have something very similar. We don't need 6. We don't need 6 anymore, because we're gonna start with 6 here, and then we have 7, 8, and 9. And again, as mentioned, we don't really need 10 anymore, because the last row will just be empty for everything. So in fact, we'll end up with the first row will start the four values. We're starting off with 13, then 28, then 45, then 64. And then starting from row 7, we have this not applicable. And then here we have 2 cells that are not applicable. And for the last row, we of course will expect having 3 not applicable. Of course, we still need to fix the A values. And then fix the A values. So starting from row 7, we have 15. Then we have 32. Last but not least, we have 51 here. Then here we have 17 and 36. And then for the last one, we have 19. Great. So these will be the A values using different U's and V's like this. Let me try to put one more here. One more. So we are going to separate into three different tables, and they are not going to be going horizontally, but vertically like this. Exactly what I'm thinking of. Great. Then now we're going to find out B and C values. Now, of course, if we're going back to our spreadsheet, this is going to be easier to calculate if we change our C values. So instead of having a minus sign, we're going to change it to a plus sign in this case. And then we're going to bring this all the way to here, and then all the way here. Now we actually get all these. And again, now all those values are positive, but then we still don't take anything that is actually below here, the diagonals. I'm going to mark it in different colors so that we actually remember there are like these are the diagonals that we're looking for. And let's see if I can actually do this. Great. So I need diagonals to be in this color. And again, the last row actually is not necessary. Again, that's because we're setting the last row be V value being equal to 10. And again, it's unnecessary. I'm going to delete this entire row. Once again, that's just because we don't need it for the V value. So again, we actually don't need this all the way to here. Oh no. We can delete this column, delete this column. I actually can, oh shoot. I'm going to delete this, delete this, delete this, and then delete this. Okay, we have 1 here. We have a 2 here. Oops, I need a 2 like that. Then it should be increasing. Okay, perfect. And again, I'm going to mark these in red. To remind us that the red ones are the ones that we don't need at all. Or I can just make it in black. I don't see it. Pretend they're not there. Okay. So now we actually get these values. Okay. So these are the C values, not the B values. Okay. So now back to the tables that we do. We have all those C values here. Again, I actually don't need this. So starting off with starting off with this here, we have we have a 5, then we have a 10, 17, 26, and then last but not least, we have 37. And again, keep in mind, don't make a mistake that like I do. And see that I put these as B values instead of C. Again, that is not correct. Don't do that. Pay attention to what we're supposed to do. We're calculating the C values, not the B values. So again, we need to fix all these problems here. Okay, be very careful. Now, second row, we have not 10, but 13. Then we have 20. We have 29. We have 40. Then the third row, we have 25. And then we have 34. Then we have 45 here. Oops. 45. And the fourth row, we have 41. And then we have 52. Last row, we have 61. Good. Next, we're going to move on to 7 to 10. So in this case, we have 50. And then we have 65. And then we have 82. Last but not least, we have 101. Then next we have 53. Then we see 60 again, and then but this time it's a 68. 77 is going to match with 85. Last but not least, we have 104. Then row 3, we have 58. Then we have 73. Then we have 90 here. There's a space here. And last but not least, we have 109. Row 4, we get 65. Is it? Yeah, 65. And then 80, 97, and last but not least, we have 116. Then we have, which row am I looking for? 65. I'm going to look for 74 here. And then we have 89. Next, we have 106, and then 125. Then for the last part, we have 85, and then for 28, we get 100. And then here we have 117, and then 136. This row we have 113, and then we have 130, 149, and then we have three more to go. We have 145, we have 164, and last but not least, I don't know why I actually put 81.9 here. That doesn't make sense. This one should just be 19. Anyway, good. Let's put it back here. If we compile it, we're going to get these. All right. Then last but not least, we need to figure out the B values. But the B values is actually the easiest to calculate because it's just simply multiplications, no addition, no subtraction. It's just 2 times U times V. So let's do the first row. It's 1 here, so 2 times 1, which is 2 times 1, 2, 3, 4, 2, 3, 4, 5, 6. So we end up with 4, 6, 8. Oops, this is not needed. These are not needed. We're running out of space here. Don't do that. Don't do that. And then here we have a 10. And last but not least, we have a 12 here. So we actually get our first row done. Excellent. It didn't exceed the sides. Second row. Well, we're going to double this value above. So 6 becomes a 12. Oh, we don't really need this. And then here it'll be 16. 20, and last but not least 24. Then here is a 2, 3, 4, so 4 times what is it? 4 here is gonna be equal to 24, and then here is gonna be 32, and here is 36. Very good. So next we have see 4 times 2 is 8, so everything times 8 is 2, 3, 4, 5 times 8 is 40, and then 6 times 8 is 48. Here is a 6 times 10, so we end up with 60. So we complete our first table finally. Okay. Now we just need to finish the other 2 tables and we're actually done for this problem. Again, it is very, it is not difficult, but it is actually tedious and a lot of calculations. Of course, the calculations are not really difficult in this case, except that we still need to, oops, this is not correct. This is 18. And then here is 20. And again, we actually do need to be careful on our calculations. But it's just basic algebra, so it's just a substitution and we'll be able to get our values out. So here it's going to be double of everything. So 28, 32, and then here's a 36, and the last one is going to be 40. Good. It's going to be triple of this first row, so it'll be 42. And then here is 16 times 3 is 48. And then next one's 54. This one's going to be 60. And the next we are going to multiply by 4. So we have 56. And then plus 8 is 64. And then here's a 72. And then here's an 80. And then the last row is going to be, the multiples of 9. So it's going to be 9 times 7 is 63. Is it? Yeah, 63. And then we have, was it 72? And then this row is gonna be, was it 81? Here's 100. And then here is the second table. Perfect. Last but not least, we have the third table. And we are still using these values here. We're gonna use the values 14, 16, and so on, okay? Or 7, okay? So times 12. We see that each time is adding a 7 here, so this is gonna be a 72. And then here I'm going to add how much from what am I trying to do? We add did I put a 72? No, this is not correct. Oops. Date. I think some values are not so correct. Right, adding a 7, adding a 7. Where did I make a mistake? This is 70, isn't it? I believe it's a 70. Let me calculate real quick. There is a mistake on the. Oh, there is a mistake on the last row here. This should be 70 already. That's why. It's adding a 14. Okay. This should be 80. This should be a 90. There we go. Problem fixed. Good. So we actually can see that there is a pattern if we go vertically as well. So 70 becomes 84. We add 14 here. And then the next one, we need to add 16. So we get 96. And then for 90, we're going to add 18 to give us 108. The last one is, of course, going to be 120. Good. Now, of course, 7 is done. Now we have the 96. Adding 16 is going to give us 112. And then next we have what? Let me take a look. We have all these values here. Okay. 108 plus 18, that is going to give us 126. And then last but not least, we're going to get 140. Then we have like a few more to go. So this is going to give us 144. And then here is 160. Last but not least, we have 180. And there we go. We actually have finally finished this problem here. Again, this problem is actually not so difficult compared to other problems that actually need some more algebra skills here. This one is just simply a substitution of the values that are given, and we just need to make our table to do the calculations here. Great. Then good. So part D. Using your table from part C, find some simple conditions on U and V that ensure that the Pythagorean triple is primitive. Well, first of all, we actually see that in order to be primitive, U and V have to be from part A, we already know that they have to be relatively prime. The GCD of U and V has to be equal to 1. And then secondly, we know that from part B, we cannot have both U and V are odd numbers because otherwise both A and C are going to end up being even as well. Then if we ignore those, so just look at when U is odd and V is even, we actually get, well, 2 comma 1 is primitive, and then 4 comma 1 is primitive, 6 comma 1 is primitive, 8 comma 1, 10 comma 1, these are all primitive. Now, if we look at V equals 2, then 3 comma 2 is, Yeah, 3 comma 2, 5 comma 2, 7 comma 2, 9 comma 2. These are fine. Now for v equals 3, we have 3 comma 4. It's good. Now 3 comma 6, of course, definitely not good because they are multiple of 3. Already broke the rule. Then if we look at 3 comma 8, this one is totally fine. 3 comma 10, this also is fine. Then similarly, if we look at row 4, we have 4 comma 5 is good. And then 4 comma 7 is also good. 4 comma 9 is still good. Row 5, we have 5 comma 6 is good. 5 comma 8 is good. And then, of course, 5 comma 10 is not good because they're both multiples of 5. Then row 6, we have 6 comma 7 good. 6 comma 9 is not good because they're not relatively prime. Their GCD is actually 3. 7, we have 7, 8 good, and then 7, 10 is also good. Okay, again, we can take the A value. We see that's the common, the prime factor of the A value is either 3 or 17. Then the other two are not multiples of 3, and then not multiples of 17. Done. 8, comma 9 is good. Because you can see 144, 145, they are relatively prime. Their difference is 1, meaning that their common factor has to be equal to 1. And last but not least, 9 comma 10 is also good. So based on the table, our condition would be the primitive, the Pythagorean triple. Again, A, B, and C, where A is u squared minus v squared, and then B is 2uv, and then C is going to be u squared plus v squared. This Pythagorean triple is primitive if u, and again, we already know uv are basic conditions. U has strictly greater than v, and then u and v are positive integers. So we need, first of all, from part A, we have the GCD of u and v is equal to 1. And second condition, u and v cannot be both odd or both even. Meaning that, again, by parity, u and v have to be one of them is odd, the other one has to be even in order to satisfy the condition. Okay, so that will be our condition here. Now again, prove that last one, prove that your conditions in D really works. So again, we don't need to prove the first part, which prove, okay, which let's see, GCD of u and v equals 1. So we can say something like the GCD of u v equals 1 is proven in part A. Then what we need to prove is we need to prove that they cannot be both odd or even. Okay. Then suppose to the contrary that both u, v are odd or both even, this implies that u minus v um, is, well, actually I can prove that plus or minus v is going to be even. It's even, i.e. 2 well, 2 is an is a factor of u plus or minus v here. Okay, why does it matter? Notice that, well, u squared minus v squared, well, actually we can do something like this. Overall, this implies that let me correct it this way. U squared or both u squared and are odd or both even, and now we actually can conclude it this way. The sum of the squares or the difference of the squares will always be even because u squared and v squared are both odd or both even simultaneously, meaning that if we treat, let's say, u squared as some other value a, okay, v squared is some other value b, then we have both a and b are odd or both even, and of course the sum of well, a plus b is going to be even, or a minus b is also going to be even, and that's exactly what we're expecting. And because of that, we don't really have to make too much conclusion here. And therefore, well, all those values, okay, all values are multiple of 2 and not primitive. And there we go. Again, since there are multiples of 2, their GCD is going to be at least 2. Okay, meaning that is greater than 1, and therefore it is not primitive. Okay, and that's how we actually end up our answers. Great. Finally, we are moving on to problem 2. Part A. Use the lines through the point 1, 1 to describe all the points on the circle. X squared plus y squared equals 2, whose coordinates are rational numbers. Okay, so what does that mean? Well, we have to first describe all the points on the circles. Coordinates are rational numbers. So we have to use some other things. So we actually get something like this. Okay, now we're gonna make it a little bit bigger. Good. So we actually want to see all those points passes through, well, all those lines passes through this this point here. Okay, whose coordinates are rationals. Now, what does that mean? So let's say we're trying to make some lines here. So if we are trying to look at this this circle here, Clearly, we have some lines such as y equals, well, we're going to put mx plus b that passes through point. So I'm going to adjust it like this. -1, then here is also -1 here, and then add slider m, and then a b. We actually, we actually don't need a b here, sorry, in order to pass through this point. Oops, I need to add a slider like this. Okay, so we now can actually see what's gonna happen. We actually get all these, yeah, uh, all these lines that we have. Well, clearly we don't really actually get uh, well, we actually can really tell much from our how should I say it, from our lines here, because these are approximation from the graph. Now, if we really want to um, describe all those points, though, like that actually satisfy that, uh, well, there are a few that actually will work. First of all, the line will not, we won't be able to adjust the slider of m to be positive or negative infinity. But if we do so, we'll actually get the strict vertical line, which actually which is x equals 1, and in this case, it will pass through the point 1 common -1. Okay, and then of course, when m is equal to 0, we get a horizontal line y equals 1, which will pass through the point what is it called, uh, what is it? It's going to be -1, 1. There we go. And of course, last but not least, we have m equals +1, which is actually going to give us the very standard um, line here, y equals x. And again, this is going to pass through the point. Uh, oops, it's going to pass through this point here. Okay. So let's try to label this point. Explore that. So we actually can see, oh no. I don't want this particular point here. Anyway. Yeah, we actually get those 3 points. Are there any others? Well, from this graph, it's not so clear, because if it's rational, we actually can try to break down into some fractions that are very large denominator, and it'll be very hard to figure out in decimals. Again, in this case, we can only point out the clear ones. So in this case, we in fact will only get those 3 points, I believe. There will be no other points that we can actually get. Now, we can actually try to prove it using algebra. So back to our document here. So to describe it, points, let's see. Passing through, describe all points on the circles whose coordinate. Of course, we should also include 1, 1 in this case. So we actually get plus -1, comma, plus -1. Again, we're in math mode here. Satisfy the condition from the based on the graph. Okay. Now, of course, these are very easy to prove, but then we can quickly try to prove it here. So we can actually try to see a proof using algebra here. So we actually just need some substitutions here. We know that in this point, this point will actually pass through the line, which is using the slope formula, we actually get m is going to be equal to the fraction of y minus 1 over x minus 1. Again, that's how we define the slope, right? Good. So in fact, if we do that, we can just multiply both sides by, let's say, yeah, just getting rid of the denominator, multiply both sides by x minus 1. So we actually get mx minus m is going to be equal to y minus 1. And if we rearrange the order, we get y is going to be equal to mx. And then we have minus m plus 1. Good. So we get something like this. Let me try to put it here. Okay. Now, of course, this is actually a scratch where we're it's like extend the from our answer. We're going to see what's going on only. Okay. Then, if we substitute back into the equation of circle, so we have x squared plus, for y, we actually end up with mx minus m plus 1. And then quantity square is going to be equal to 2. Great. So if we expand out, we have m squared times x squared, of course. And then if we combine it, we actually will end up with this x squared. And then we have minus 2m plus 1, or well, in this case, it's going to be plus a negative 2m plus 2 times x here. And then we finally have the m minus 1 quantity squared. So that is going to give us m squared minus 2m. And then we have a plus 1 to be equal to 2. So if we're going to move the 2 to the left side, we're going to end up with something like this. So we actually get the condition like this, and then now we actually need to try to solve it. Solve for x, of course, in this case. Well, we know that one of the values of x must be equal to 1. 1 will always satisfy it. So if we try to solve for x, we will get, using the quadratic formula, we have what is it? We have b negative b. In this case, it's going to be 2m plus minus 2, and then plus or minus the square roots of b squared. So b squared is going to be the square of 2m minus 2, so it's going to be 4m squared minus 8m plus 4. And then we're going to subtract 4ac. 4ac like this. And then, of course, the denominator here is going to be equal to 2a. Where was a? M squared. So it's going to be 2 times m squared plus 1, like this. Okay. Now, of course, we can actually try to factor a lot of things. We can, first of all, factor out the 4 inside the square roots, and then it will turn out to be a 2, and then factor out the 2, we actually will get something very similar. And again, our goal here is not trying to solve for, or just solve for, not directly solving x, but our goal is to trying to make sure that x is going to be a rational number, which in this case could be will always be equal to 1, but it will also give us different answers based on the m values. If we change our m values, we'll actually end up with different answers too. So here we actually get this, and then we actually take this out, and then for the m squared, the m squared plus 1 times the m squared minus 1 minus 2m, that part, this part here, Let me try to put it a little bit closer. Yeah, wider like this. Okay. This part here, if we try to simplify the everything inside of the radicals, we of course will actually get something not too nice. So what do we get? Well, we actually get here. We get this part is gonna give us something very ugly. We have m to the fourth power minus 2m to the third power, and then we have the m squared part is actually cancel out somehow, and then don't forget the negative sign. So we actually get plus here. And then here we have negative 2m, but then change it to positive. So we have positive 2m. And then finally we have a plus 1. Okay. We have something like this. And then after that, we're going to simplify. So we have negative m to the fourth power. That part stays. And then we have 2m to the third power. That part stays. We have a positive m squared from here. Good. And then the negative 2m and the positive 2m canceled out. And then last but not least, we have plus 2. We have some crazy thing like this. Okay. Of course, we can see that if m is equal to 0, this thingy, well, let's refresh it. Where'd they go? Oh, there we go. So if we recompile it and get this part here, we see that this is blocking my way. Okay, there we go. So we see that if somehow we actually get our calculation incorrect, but anyway, yeah, it's basically the goal here is trying to show that. So well, what do we have? B squared minus 4ac. Factor this out. This is good. This seems not really a big problem here. But anyway, yeah, or if we're trying to follow it, we actually have to force some other m to be some special values here, to make it work. But like anyway, we kind of see that there are only like a few m values will actually make make this part being very nice to get the rational. Of course, this is just a concept here that we're going to use. We're not going to prove it. But anyway, this is how we actually see that there are only like a few points will actually work. Okay. Now, what goes wrong if you try to apply the same procedure to find the points on the circles x squared plus y squared equals 3 with rational coordinates? First of all, it's not possible. We have actually proven that there's no we cannot pick any point to that's being rational. So for the last part B here is our solution. We cannot find any rational points. Well, any point whose coordinates are rational numbers. If we're trying to again, the idea here is that because we're going to replace the replace the y in terms of m was it m times parentheses x plus some x minus something, and then we have plus some other things, or we in other words, if we want to find a line that actually pass through that the point, we actually need to find points such that uh, is rational, and then using that to find other rational numbers, we can use the slope formula, m equals y minus the y coordinate y naught over x minus x naught, and then doing all those algebra again to find out other points. But then the first step, uh, which is pick a point whose coordinates are rational, cannot even be done. Um, since again, that is because if we are trying to do some kind of do any kind of substitution, replace x by a over b and y by c over d, for example, okay, because we are saying that they're rationals. Then again, a, b, c, d are integers, and a and b are relatively prime, c and d are relatively prime as well. Cross multiplying all those stuff, we should end up with AD quantity square plus BC quantity square is going to be equal to 3 times the square of the denominators, BD, okay? Then, of course, we can now substitute with some other variables. Let's say call, some other letters. U, and then V, and then W. Then we have U square plus V square is going to be equal to W square, where U and V are positive integers. Now, the problem is that uh, we actually have tried by like in chapter in the beginning of chapter 2, we have tried to show that by parities, uh, if it, if we are trying to take everything in mod 4, meaning that if we are trying to divide u by 4, v by 4, and w by 4, we should actually end up with u squared is either equal to 0 or 1, v squared is also either be equal to 0 or 1, and then w squared is also either be equal to 0 or 1. Okay. Now, again, we know that we can try to bring down so that u, v, and w have no common factor, so that now we will say we'll be able to see that we cannot have u, v, and w are all gonna be congruent to 0 mod 4. So in that case, we have at least one of the u and v gonna be congruent to u square or one v square is gonna be congruent to 1 mod 4, meaning that the left hand side is gonna be ending up with either 1 or 2 mod 4, but then the right hand side is either gonna be equal to 0 or 3 mod 4. And there is no way we will be able to get the left hand side is going to be equal to right hand side, and therefore, like uh, from chapter 2, we showed that there is no u, v, w. We'll say positive integers in this case. What am I doing? Where did they go? Where am I? Find formula. Why would it pop up? Let me see. There it says conditional rational. Okay. Oh, I pressed the page up. That's why. In integers with u, v, well, the GCD of u, v, w is going to be equal to 1. Set this find u squared plus v squared is going to be equal to 3w squared. Find in. This is a G, not F. By again modular arithmetic. Okay. So we cannot find any points, and to actually apply the tool, using a line to describe the points with coordinates rational numbers. Okay, good. So finally, we finished problem 2. Now this time we're going to change from plus to minus. So we have hyperbola. Okay. Oops. There we go. Find the formula for all the points on the hyperbola x squared minus y squared equals 1, whose coordinates are rational. Take the line, and here's a hint, take the line through the points -1, 0 having rational slope m, and find the formula in terms of m for the second point where the line intersects the hyperbola. So let's do it. So let's see. Begin our solution here. Well, what do we need? We have m is, we're going to use the slope formula. So we have y minus 0, the y value, then x minus -1, which again is going to be equal to the fraction y over x plus 1, it be the line passing through the point -1. And let's try to rewrite this m. Well, we know that as a rational number. Let's call it a over b. Okay. For some a being this. Oops. Being an integer, it could be negative at this time. Okay. And b is a positive integer such that the GCD of, again, a and b, we put the absolute value because, well, usually we can say that GCD is -1, but when we talk about GCD, usually we expect a and b are non-negative integers. So it could be including 0 in this case. By the way, if it's 0, if that means that a has to be 0, then b has to be equal to 1. Okay, because we want to simplify our fraction for m. Okay. So if we're trying to write this way, we actually get by rewriting the linear function, we have, well, of course, in this case, we have y is equal to mx plus m. Okay. What do we get? Well, we actually get, now we're going to substitute it. just like what we kind of showed in problem 2a. Okay, then we have x squared minus this quantity here, m x plus m squared equals 1. Okay, and again, we'll do something like this. All right. Then what does that do to our parts? Well, remember, we're trying to uh, find a formula in for it, and then in terms of m, right? Okay, and we don't have to write it in terms of a and b. Oh, well, yeah, we just need to leave it as m. Okay, then in this case, we're going to solve for m. Well, I mean, sorry, solve for x. Okay. Um, then what do we get for that? We have x squared. Well, in this case, we're going to factor everything. We have 1 minus m squared times x squared. Um, and then we have minus 2 mx. And then we have minus, oh, well, yeah, plus negative m squared. And then we move the 1 to the other side. We have minus 1 equals 0. So we can actually, in fact, just try to multiply everything by negative 1. In that case, instead of 1 minus m squared, we have m squared minus 1. Then here we end up with a plus, and then here we end up with m squared plus 1. Now, does it look familiar? Yes, it does, because what happened here is, remember, we call it m is some rational numbers a over b. So, or we can rewrite or replace it with u over v. This actually might actually help us understanding it. So if you replace it by u over v here, we have u here and v here, of course. V here, we have u. Well, in this case, if we try to think of our substitution here, replace the m by u over v, and then here and here as well, and then multiply all the denominators by v, multiply by the denominators v squared. So we end up with u squared minus v squared. Here we end up with 2u over m times v squared, which is 2uv. This part is going to end up with u squared plus v squared, which is exactly the form of the Pythagorean triples that we have in problem 1. Okay, so here we actually just have something very similar, but again, the goal of this problem here is to solve for x, though. So we just want to simply throw in those quadratic formula. So we end up with this, and then we have a square root of 2m squared. It's going to be 4m squared. I know, sorry for English. This is how it works. When it says 2m squared, we'll actually need to do quote unquote. So we know what does a square include, okay? Well, it's a square of the quantity 2m, okay? Then it's going to give us 4 times just m squared, okay? Anyway, too much of an joke here. So next, we're going to multiply by 4ac. So if we multiply by 4ac, we actually end up with m squared plus 1, m squared minus 1 is actually a difference of squares, so ending up with just m squared, so it'll be m to the 4th power minus 1 here. And then last but not least, we have 2 times a, well, 2a here on the denominator. And again, we can actually factor out the 2 to give us negative m plus or minus the square roots of m squared minus m to the fourth power plus 1. And then and then we will have where did the mistake go? Let me see. Minus here. I don't see a mistake here. M squared minus 1. Something like that. Okay. So we should end up with x is equal to something like this. And then once again, oh, here's a problem. Here should not be 2m, but 2m squared. That's the mistake. Square. And again, that's because we actually multiply the mx times m. So we should end up with squared. So if we do that, now we actually need to fix our stuff here. This is the fourth power. Here is m squared. And then we actually end up with this. And then we actually end up 4 here. But let's refresh it. Now we actually see what's going on, because the m to fourth power and m to fourth power are actually will actually cancel out to end up with just square root of 1 here. So I'm going to leave it like this. Good. So square root of 1. Of course, we actually can take out the square roots as well. So we actually will get the following. So if we take the plus sign, we either end up with negative 1 with the plus sign, or actually, I'm going to do something like this, or with comma, which is actually commonly seen. Negative m squared, negative m squared plus 1. Then here on the denominator, it will be m squared minus 1. There we go. Excellent. So we end up with 2 different x values. Okay, something like this. Right. And that's how we actually end up with our solution. Okay. So we now have problem 4 and problem 5. Let's see how many more. Yeah, just 2 more problems. Hopefully, we will definitely won't be able to finish it by today. Hopefully, we'll be able to finish the last 2 problems in the next live. We probably will be able to do it though. By the way, yeah. So let's try to go over this problem. Hopefully, we can try to finish one more problem before this stream. Let's see. So problem 4, the curve y squared equals x to the third power plus 8 contains the points 1, negative 3 and negative 7/4, 13/8. The line through these 2 points intersects the curve in exactly 1 other point. Find this third point. Can you explain why the coordinates of this third point are rational numbers? Well, we can actually try to brute force it somehow, but it's actually not so good idea. So we are going to not substituting these 2 in, because once again, we can't really do factoring out easily like a cubic function, because we don't have an explicit y values. But in fact, we can actually write y equals plus or minus the square roots of the right hand side. Okay, meaning that if we're trying to put in the x values, we will end up with 2 y values, and we can really do solve it that way either, because in fact, if it works for 1 comma negative 3, we also know that it works for 1 comma positive 3. Similarly, if we actually find another one, we use another point, we actually will end up uh, with with the negative value of it. But then it doesn't help us to know the third point that is actually on this line. So might as well just try to start with the linear equation or the linear function. Let oops, not begin a line. Sorry, it's gonna be a solution. So let's we'll again say that y equals mx plus b be the line that contains or containing 1 comma negative 3 and the other point negative 7 over 4 13 over 8. Okay, and then the slope, which again we can use the slope formula. And this time when we use the slope formula, we're gonna use not just y and x in general, we're gonna use y1 and x1, y2 and x2. So we have, let's pick the first point, which is 1. Well, actually 1 is the x value, so it'll be on the bottom. Then the y value is negative 3. So subtracted to the second point, which gives us 13 over 8. Again, we're already in the math mode, so might as well put in fraction. And then we have fraction of negative 7 over 4. Oh, here's a mistake. Be careful to the sign. It's going to be very important to our calculation. So if we try to solve for this fraction here, let's see what we have. Definitely we get a fraction back. Negative 3 down here. Negative 3 minus 13 over 8. So we will still end up with negative. And then, not gen fraction again. We have 3 is equal to 24 over 8. So 24 plus 13 is going to be 37. That's the numerator. The denominator, we have 1 minus a negative, so it turns into plus 7 over 4. So that is going to give us 11 over 4. And again, we just need to multiply both top and bottom by 8. That's a common denominator. So that we end up with we still end up with the negative sign outside, by the way. We have 37 here, and then the bottom is going to be 11 over, times 2 is going to be 22. So the linear function is, now we actually have the oops. Well, we actually can say something like this. Solving the linear function, we obtain, well, now we are going to talk about the linear function. We have y is going to be equal to what is it? What is the fraction again? Negative 37, 22 with a negative sign. And then plus b. Now again, this actually makes sense because we actually don't know the point. We actually need to find out actually we can find out the b value. yeah, we actually can find out the b value. So how do we find a b value? Well, we actually know the 2 points, right? We can use one of the points. Let's say 1 comma negative 3. Then, and then we can say that it implies that negative 3 is going to be equal to negative fraction 37 over 22 plus b. And then if and only if b here is right, we're going to have something equals b. We're adding the fraction to the other side, and then we're going to rewrite it back as b equals that fraction. So we'll be negative 3 plus the fraction, where 3 is equal to 66 over 22. So we end up with 66 minus 37. That's giving us 29. So we end up with negative 29 over 2. And then implies that we have implied by the way, huh? Okay. Implies our equation y is going to be equal to negative negative well, we can write the entire thing as fraction because they have the common denominator 22 there. And then we have 37x, and then we factor out the negative already, so it turns into positive 29, like this. Good. Okay. So a few more minutes, and then we have to stop. It'll be 2 hours. So let's see. We have like 3 more minutes. Hopefully we can try to get this done, by the way. So we actually end up with this linear function. Now we need to substitute the curve in order to find out the third value. How do we do that? Well, again, it's just a substitution. So we're going to replace this to the left-hand side. This provided us the left-hand side is y squared. So we end up with we have the fraction still. It will be square of this thing, but negative square is positive, and then we just square the denominator and the numerator and denominator respectively, like so. And then we have 22 squared, which is 484. That's going to be equal to the right-hand side, which is x to the third power plus 8. And then if we try to get rid of the fraction by multiplying both sides by 484, and then throw everything else to one. Flip the two sides, and so we have 484 x to the third power plus 484 times 8. That is gonna be what, 22. Let's see, 88 squared. Is it? No. 22. Oh wait, hold on. No. 88 square. No. 44 square. No. It's gonna be 44 squared times 2, which is 1936 times 2. That is 3872. So we end up with 3872 here. It's equal to the numerator of the fraction. So we have 37 squared, which is 1369 x squared plus 37 times 29. That is going to be close to 37 times 30, which is 1110 minus 37. That is going to be 1100 minus 27, so 73, 1073. And then multiply by 2, we're going to get 2146. 46x plus 29 squared, that's 841. Now we're going to move everything to the left side. So we end up with something like this. Of course, this is actually pretty bad because we're actually brute forcing a lot of stuff. but hopefully we will be able to simplify a lot during the calculation. Well, there are actually two things that we know. First of all, we know that that's 1 comma -3 is our solution, one of the solutions, and then we actually know the other solutions, meaning that in fact we actually know that two of the x values, 1 and -7/4. So we can actually use those two as our factor to find out the last factor. Okay, so if we continue our calculation, we end up with 3031, which is actually quite ugly. It's going to be equal to 0, by the way. If our calculations are correct, then we'll be able to factor a lot. So knowing that x equals 1 and x equals -7/4 are solutions of the above equation. We're gonna do prime factorization. Okay, so what are we gonna do? We're gonna use our old friend. We're gonna, well, somewhat cheat a little bit. Let's try end this quick. We're gonna use Wolfram Alpha to help us to figure out the factorization of this, instead of trying to write the steps. But we should actually expect that this will actually give us 3 factors: x equals 1, x minus 1, and then 4x plus 7 as expected. And then we actually end up with the last part, 121x minus 433. So the remaining solution would be so let's see, we have this here, 121x. Let's try to end up with 121x. Did I say minus or plus? 133. It's going to be equal to 0. Or in other words, there's nothing we can factor out, by the way. X is going to be equal to, this is a positive value, by the way, 433 over 121. Which means our y value, y value is going to be equal to, again, we have our fraction up here, negative fraction of 37 times another, well, c dot, another fraction. What do we have? 29, and then we have a plus 29 here, 22 down there, right? We have 121 on bottom, and then we have 433 on top, like this, and then we're going to simplify it. So we need our calculator here. Calculator. So what do we need? We're going to multiply both top and bottom by 121, of course. what's it called, the denominator. So on bottom, we end up with 121 times 22. That's going to give us 2662. 2662. And then on top, we have 37 times 433 plus 29 times the denominator, which is 121. So we get this value here, 19530, 19530. Okay, and then last but not least, we're going to rationalize it, meaning that we're going to, again, we're share it. We're not. Oh, we're almost done with this part. Rationalizing it. We're going to use our old friend Wolfram Alpha to help us in doing the computational work. So we have fraction of what did we get? 19530, 9530, and then over the other fraction is 2662. Okay, that's so strange here. Anyway, I'm sharing it here. Okay. So from alpha, this is, as we try to simplify, well, we can only factor out 2 here, unfortunately. Then if we try to factor out the 2 or divide both top and bottom by 2, we get 9765. Divide by 1331. Okay. And therefore, to here, back to our answer. Therefore, the third point is, well, we kind of need the what is it called? Well, it doesn't matter. We can actually write like the second point. 433 over 121, no, 131, okay, comma, negative 9765 over 1331. And the last part is saying, explain why the coordinates of this third point are rational. The coordinates of this third point must be rational numbers because how should we say it? Well, we end up with all rationals, right? So it's very obvious that the slope of the linear function is rational and the 2 other points are rational. And in order to have the products being rational, in order the coefficients of the curve, given curve being rational, not rations, rational, the quotient which is the quotients which are the coordinates of the remaining points has to be rational. Have to be rational. Otherwise, we have irrational times rational, which cannot be rational. Times non-zero rational, which cannot be rational. There we go. Okay, so we have finally finished this problem, and we actually went over time already. So here again, this is a solution that we get, including the answer that we need. Why we should expect that this coordinates have to be rational. So next time we're gonna finish in the last problem, problem 5. We actually see that there are 6 parts. There is actually a lot, and we're gonna spend the entire time on this problem here for the next life. So after that, we'll actually finish chapter 3 already, and then the time after next, we're gonna start chapter 4. Okay, thank you for watching. I'll see you guys in the next stream.